Okay, in this video, we continue our logistic regression. We've already brought in the data. We're trying to determine if we can predict if someone's going to buy a house based on some information. And what we focused on was if we know their income, how old they are, and what part of the world that the house is, the zip code of the house that they're buying. So once we've got the data in, now we're going to go under analysis, and we're going to go under regression, and we're going to go under logistic regression, the two outcomes, because we only have two outcomes. We only got zeros and ones. And what pops up is this is how you build your model. First of all, you have to decide what is your variable, your Y variable, your dependent variable. Well, that's if they purchase or not. And if you notice up here over these, this tells you that particular column is continuous, and then these tell you if they're categories. And just to let you know is that if it's continuous, you need to put those in the covariate box. If they're this, that means they're factors. Now, age is one of these weird ones. It can be in both because age is actually continuous. It's just that it didn't recognize it as continuous because there's no decimals. But look what we're going to do. First thing I'm going to do is bring purchase over as my dependent variable. And just like that, you can see that things start getting built. So this script is being built. So the first thing I'm going to bring over is my income. So I'm going to click on it, and I'm going to say, well, what is the predictor with the ability to predict purchasing as a function of income? And it automatically starts doing the analysis. And a couple things that you get out of this is that you get a model fit. Just like R squared in regression, there's the McFadden R squared, which is similar, and you can interpret it the same. So income accounts for 23% of the variability of why someone would buy a house, and that's a large chunk. We can see also the actual predictor values. We'll use these later when we build a calculator to predict the likelihood, but for now, that's really all you have to do is bring things over. So you can see 0.227. I'm going to take it out. I'm going to bring in age by itself. And when you bring in age, you can see the R squared is really, really small, and my p-values attached to age are really big. Short answer, it doesn't look like age is a factor to influence. And I could have dropped it there, which is where it should be, but I could have also dropped it there. The last one is zip code. Zip code, it is truly 0-1. You don't want to bring it there. You want to bring it into as a factor because it is a 0-1. It doesn't represent 0 and 1. They're not numbers. They're categories. So bring it in as a factor. Once you've done this, you can see there is an R squared that's bigger than 0, and its p-value is actually small. So it is influential. So if I was going to build a model, it looks like income and zip code are the ones that I would want to use. But you can bring them all in. This is if you've brought everything in, all three models. There's your R squared. And you can now look at these as look at them all at the same time, and you can see the one with the smallest p-value is income, and then zip code, and then age is not significant. We'll talk about the estimates and how we generate our logit model in a minute, but I just want you to show this is the analysis. So what we're doing is trying to make this as big as possible. The biggest this can be is 1. But I would say right now you've got a model that's a pretty good start. If you get an R squared of 0.4, 40% of the variability, 41% of the variability is accounted for. The smaller the p-value, the more influential it is. So income is more important, and this is the coefficient for that. So income and where the house located it predicts if someone's going to buy a house or not. Let's look at these things over here. And some of these are more advanced, I don't want to go over, but model builder, don't worry about that. I'm not interested in that. Reference levels, don't worry about that. Assumption checks, let's not worry about collinearity. This is important in multiple regression. I don't want to worry about it now. Model fit. So what we're using is the McFadden R-squared. There's other R-squareds by different mathematicians. I don't care. You can, if you want to get all of these, you can see what they all are, and you can see how they change if you want to. That's fine with me. I don't use the AIC when I report things. I can turn that off. Model coefficients. I don't worry about. I don't worry about this one. Prediction. This is a good one. Prediction. Let's look at this. Remember what you're getting with this equation, and we'll talk about this equation. It's going to generate a probability. It's going to generate a value on this orange curve based on what your x's are. In this case, we got 3 different x values, so this is a 4-dimensional problem. So what you get, your p-value, this p that's calculated is a probability. Right now, it's set arbitrarily that if that p is larger than 0.5, then it becomes 1, it rounds to 1, and if it's less than 0.5, it rounds to 0. And if you remember from the data, we had some zeros and 1, where 0 meant they did not purchase, and 1. So when we get a prediction and we use a cutoff, if we get a p of 0.4, then it will be, the model will say, or the way it's set up right now, it means that they did not purchase the house. But we can change that. We can change this cutoff value, and one way to do this is doing this. Look at this and see the dotted, where they cross is probably where this should be. So you can leave it there. You can change this to like that. That's probably not where it needs to be. It probably needs to be where these line up. So let's not do that. Let's go ahead and keep it at 0.5. Like that. Okay? Maybe a little bit higher is where these cross, but it's kind of tough. This isn't something that's easy to figure out or what the best thing to do. So I'm going to leave it at cutoff value 0.5. The other thing that becomes important is this classification table. So let's grab that. So this is an understanding of the data that we had. Remember, we had 30-something data points. 36 data points. And those 36, what would happen is that when it was 0, the model predicted 0. The model, based on what we've done, predicted correctly 18 times. There were 4 times it didn't do it correctly. This is what really happened. The model said, oh, they bought the house. So the probability of predicting if they're going to not buy a house is 81%. Well, that's pretty good. If you compare this to 50-50, it gives you it's pretty good. Now this is if they buy a house. This is if they did not buy it. This is if they bought it. Well, if the model said that they did not buy a house, that's an error. So there were 3 out of 14 mistakes. But there were 11 out of 14 where what really happened and what the model said happened were correctly. So there's your 78.6. So look at these. Excuse me, not that. Specific, I can't say the word, and this, the 81.8, this right here is the specificity. And then the sensitivity is this one, which is this. So the definition of sensitivity is when it predicts when something yes happens and the model said that it happened. Specificity is when something did not happen and the model says it did not happen. So that's what, and then the overall accuracy, it predicted correctly 18 plus 11, if you add that up, divided by 36, 18 plus 11, Divide by 36, it gives an accuracy of 80.55. That's what this number is. Right there. So you can grab all that from that, but if you wanted to report it, there's it. Now you can change the cutoff value. So let's go put this at 0.3. And you can see what happens. The overall accuracy went down, this went down, this went up. So it becomes what's important to you. We can maybe make this 0.55. And we got a little bit better, I think. I can't remember if these were better or not. So this is just other ways to do this. I'm going to leave it at 0.5 now. That's where I'm used to seeing it most of the time. Okay, so these curves, this is, I'm not going to go over these, but this is the output that you would get when you did your analysis. And you need to talk about what they are and the understanding of what these are, analysis and model fit. Thanks.